Hey guys, I hope you're doing well out there. I'm excited to see what you came up with for your at-home chemical reactions. I hope you kept it safe, kept it food grade, and maybe even made something tasty, or got a little creative with it, made something not so tasty. Today we're going to be talking about ionic bonding and synthesis reactions, so let's jump into it. First of all, some learning objectives. I can write the formulas of neutral ionic compounds based on elements' ion charge. I can predict the products of simple synthesis reactions. And I know what the diatomic elements are. Probably should have been included in the periodic table slideshow, but I forgot to put it in there, so I'm just going to backfill a little information on diatomic elements. All right, so first, just a recap of ions. Recall that ions are atoms with a non-zero charge. Positive ions are called cations. Here in this graphic, we can see helpful reminder is think of the T in cation as a plus sign, or my personal favorite, remember cations are positive, like a cat in pause, and then anions are negative. And here, this graphic reminds you that anions has an N in it, and that N corresponds to negative. I don't have a fun little cat play on words for that one. Ions form when atoms lose or gain electrons to eventually have a full valence shell, and that's called ionization. And the charge of an element's ion is easily predictable based on its location on the periodic table, and that's for S and P block elements alone. We're going to not get into D block transition metals, so we're just looking at the S and P block elements. And you can see here in this graphic, I've got sodium, a neutral sodium atom. It's got 11 protons, it's its atomic number. It's got 11 electrons if it's neutral, and it's got one of those electrons in the 3s1 subshell. So it's got one valence electron when it's neutral. If it could only get rid of that one valence electron, it would empty the energy level number 3, and that would leave it with the 8 in the second energy level, which is a full valence shell. And that losing of one electron gives it a positive 1 charge, and so that is how sodium ionizes to fill its valence shell. And here's just a helpful reminder, you're definitely going to need a periodic table for this, and you're going to need to keep in mind these numbers above the columns, because that will be very important. And you can see that sodium here has one valence electron, like we just said, as do all the members of this column, this group. And so that means that it just needs to lose that one valence electron to fill its valence shell, and that is the explanation of why all of these members have a +1 charge. So let's get into what ionic bonding is. If an element loses an electron, the electron must go somewhere, and the likely place for the electron to go is to an element that needs to gain an electron. This means that cations and anions are often created at the same time in something we call a synthesis reaction, which we'll get into in just a second. The positive cation and the negative anion are then attracted to one another because of their electrical charges. And for that, just remember that old fable, opposites attract, that comes from electrostatics. A positive charge is attracted to a negative charge. When these ions are held together by the attraction of the opposite charges, we call that ionic bonding. So bonding means being held together. Ionic is referring to the fact that they're ions being held together. So here we can kind of see an example of that. Sodium wants to get rid of one electron. Chlorine wants to gain one electron. Sodium transfers its electron to chlorine. Now sodium's got a +1 charge. Chlorine's got a -1 charge. Each has a full valence shell, so they're stable. And that +1 of sodium is attracted to the -1 of chlorine. So a metal, a cation, and a non-metal, an anion, held together by ionic bonding is called an ionic compound. In that last example, sodium's a metal, it forms a +1 cation. Chlorine's a nonmetal, it forms a -1 anion, and so that attraction between +1 and -1 creates the ionic compound sodium chloride, table salt. The other, just as a quick aside, the other major type of bonding is called covalent bonding, which is when electrons are shared between atoms of nonmetals only. So here the key differences are the electrons are shared and it's only nonmetals. Whereas in ionic compounds, it's a metal and a nonmetal, and the electrons are completely transferred. One loses and the other gains. An ionic compound must always be neutral. I can't stress this enough when it comes to writing formulas. The overall thing has to be neutral. In other words, all the positives have to cancel out all the negatives. Compounds bond at different ratios depending on the charges of the cations and, that's supposed to say anions, to make sure that they cancel out overall. All right, so you got to balance the total charges of the positives with the total charges of the negatives to make sure it's equal. Ionic compound formulas are always written with the cation first, the metal first, and the anion second. And cations are on the left side of the periodic table, anions are on the right side, so you could remember it that way. The thing from the left side and then the thing from the right side. And then lastly, simple, and by simple I mean two-element ionic compounds are read as the cation's elemental name, and then the anion's an elemental name, but the ending on the anion is changed to IDE. That's why instead of saying with sodium chloride, NaCl, we don't say sodium chlorine. We change that ending to IDE to represent an anion, and then we say sodium chloride. Definitely something that'll take practice, so we're going to jump into some of that practice. Here's an example that we just talked about of sodium bonding to chlorine as a model. Sodium's one valence electron will go to chlorine's one valence hole, as I call it, and both are going to then have a full valence shell. Sodium's one layer down, chlorine's just where it is. And that one sodium with the one valence electron is able to fill one chlorine with one valence hole. And that's why in the end, the ratio here is 1 to 1. For every one sodium, we have one chlorine, and the formula overall is NaCl. And then again, we read that as sodium chloride. We're changing the "-ine" ending of chlorine to "-ide" because it's in a compound. Here's another example. Here we're dealing with magnesium and oxygen. Magnesium in the second column has 2 valence electrons. Oxygen has 6. It's in the 16th column, which means that it has 2 valence holes. So what does this mean overall? It means that one magnesium with 2 valence electrons is able to fill one oxygen with 2 valence holes. So even though the charge of magnesium is +2 and the charge of oxygen is -2, it's still a 1 to 1 ratio because the one magnesium cancels out the one oxygen. So in the end, we get a formula of MgO, and we would read that as magnesium oxide. Again, not oxygen. We change the ending to IDE. There's another example, a little more complex. Now we're dealing with sodium and oxygen. And so what do we have here? We have 2 sodium atoms with 1 valence electron each are able to fill the one oxygen with 2 valence holes. And that would ultimately give us the formula Na2O. Na2 because it took 2 sodiums for every 1 oxygen. And then even though there's a 2 there, I'm still going to read this like we've been saying. I read the cation's name, sodium, and then the anion's name with the IDE ending, oxide. So Na2O or sodium oxide. One more example. In this one, we're dealing with magnesium and chlorine. Magnesium, as we said, second column, it's got 2 valence electrons. If it's bonding to chlorine, then one of its valence electrons can fill a chlorine, and the other one can fill another chlorine. And then again, everyone's got a full valence shell. So in this case, one magnesium with 2 valence electrons is able to fill 2 chlorines with 1 valence hole each. And so the ultimate formula there would be magnesium, or it would be MgCl2 because I have two chlorines, and the name would be read magnesium chloride. So hopefully that just kind of theoretically gives you some examples of where these formulas come from in terms of electrons being transferred from cation to anion. We'll get into just kind of a general procedure for writing ionic compound formulas and names. So the first thing I want to do is write the cation with its positive charge. Where do I find the charge of the cation? I look on the periodic table. If it's in that first column, it's +1. If it's in the second, it's +2. Skip the D block. If it's in the third, it's +3. Next, I'll write the anion after with its negative charge. Again, I look at the column it is in the periodic table, and I look back to these numbers, and I'm able to identify what the charge of that anion would be. If it's nitrogen, it's -3. If it's oxygen, it's -2. If it's fluorine, it's -1. And those patterns ripple down through the column. And then, is the charge neutral? That's the question I ask myself. If so, I'm done. And if not, I need to add another ion for whichever you have less of. So if I have less positives, I need to add another cation. If I have less negatives, I need to add another anion. And then I ask myself again, is the charge neutral? If so, you're done. And if not, I need to add another ion, again, for whichever I have less of. And I just kind of continue this process until I get to a compound that is totally neutral. All of the positive charges added up are equal to all of the negative charges added up. I'll give you some examples in just a minute. Next, once I've kind of added ions until the charges overall cancel out, I can count up all the cations that I had to add, and that's my subscript for the number of cations. And then I can count up all the anions I had to add, and that is my subscript for the number of anions. Lastly, I write the complete formula with those subscripts. Note that in the formula, because the overall thing is neutral, I do not include any charges. And then to write the name, I would name the cation, and then I would name the anion using that IDE ending. All right, so we looked at this. We already know that it takes 1 sodium for every 1 chlorine to form sodium chloride. Well, let's look at that procedure we just talked about. I write the cation with its +1 charge from the periodic table. I write the anion with its -1 charge from the periodic table, and then I ask myself, is it balanced? And in this case, yes, it is. +1 cancels out -1, so it's balanced. And so the subscript on each of these is 1, because I only had to add 1 to balance it. And therefore, I just write the formula NaCl, not including the 1s, because if nothing's written as a subscript, it's assumed to be 1. And that is sodium chloride. So let's do another example with that procedure. I start by writing the cation, in this case magnesium with its +2 charge. I write the anion, oxygen with its -2 charge. Again, those numbers come from its location on the periodic table. And then I ask myself, is it balanced? In this case, yes, it is. And therefore, I don't need to add any cations or anions to get to a balanced compound. And so my ultimate formula is MgO. Why? Because I only have 1 Mg to cancel out 1 O. Here's another example that we already looked at. We know the formula is going to be Na2O, but here we again write out the cation +1 with its +1 charge. We write out the anion with its -2 charge coming from the periodic table. And I ask myself, is it balanced? And in this case, no, it's not balanced to begin with. Negative has more. It's got -2 versus +1, so I need to add more positive to try to counter that. So I add another sodium ion, and now my total positive charge, when I add up both of these +1s, is +2. And the +2 of 2 sodium atoms, 2 sodium ions, is able to cancel out the -2 of 1 oxygen. So now it's balanced. So when it goes to writing the formula, I ask myself, how many cations did I have to add in total? I have 2 cations. How many anions? I only have 1 anion. So that's why I'd write Na2O. All right, last example. I write out my cation, magnesium, with a +2 charge. I write out my anion, chlorine, with a -1 charge. I ask myself, is it balanced? No, it's not. +2 is greater than -1. I'm more positive than negative. So I add another negative, another chlorine ion, and now my total negative is -2, and so that is balanced. From that, I can write the formula, and here I have 1 magnesium for 2 chlorine to get it to be balanced, so my formula is MgCl2. So that is one surefire way to get to having ionic compound formulas, writing ionic compound formulas. Here's a shortcut, and it works like this. I call it the crisscross method. Write the cation with its positive charge up in the top right. Write the anion with its negative charge in the top right. And then crisscross by bringing the anion's charge down to be the cation's subscript, but you make it positive. You can't have a negative amount of atoms, so you have to make it positive. And then take the cation's charge and bring it down as the anion's subscript. Here's what I mean by that. In this case, compound is lithium oxide. Li's got a +1 charge because it's in the first column. O it's got a -2 charge because it's in the 16th column. And so when I crisscross them, I bring the 1 down from lithium's charge, to be oxygen subscript, and I bring the 2 down from oxygen's charge to be lithium subscript. And my ultimate formula, that would get out of the way, you can see is Li2O. Another example here, I write out aluminum with its +3 charge, write out oxygen with its -2 charge from the periodic table, I crisscross them, and that's going to give me a formula of Al2O3. You can check to make sure this works by writing them out as individual cations in a list and anions in a list, and then adding up the total charge on each side. But it does work. Works all the time. So that's one easier way to do it. Now that we know how to write ionic compound formulas and simple ionic compound names, we'll get into a synthesis reaction. You read a little bit about reactions in the last assignment. And so we're going to apply this idea of making ionic compounds to the chemical equations that you read about. A synthesis reaction is when two simple substances, like elements, react to form a single compound as a product. So in this case, this general form, I have element A reacts with element B to form compound AB. And this could be a metal that's going to form a cation A, and a nonmetal that's going to form an anion B to form the ionic compound with cation A and anion B. If a metal reacts with a nonmetal, it will form an ionic compound with the formula expected given each element's ion charge. What I mean by that is, when I go to do these reactions, if I have my elements, A plus B, I need to consider what charge will A take, what charge will B take, and use those charges to figure out what the final formula is. We'll look at an example in just a second. For those of you out there who want to include phases as an italicized S, L, G, or AQ after, know that the product in a synthesis reaction will pretty much always be solid. You could just always say it's solid because ionic compounds have an extremely high melting point. They're almost always solid. So here's an example. Let's say I give you lithium reacting with sulfur, and I ask you to complete this reaction. Well, lithium's a metal. It's in the first column. Sulfur is a nonmetal. It's in the same column as oxygen, the sixth column. And so I write out the charges of each. Lithium's going to get a +1 charge when it reacts. Sulfur is going to get a -2 charge when it reacts. And I can crisscross those. I'll bring the 1 down to be sulfur subscript. I'll bring the 2 down to be lithium subscript. And I can get a final formula of Li2S. So if lithium reacts with sulfur, it'll make lithium sulfide, which has a formula of Li2S. Hopefully that makes sense. These are your PD questions, is trying to predict the products of synthesis reactions. All right, and then the last piece, and I'll be real quick about this. When we were studying the periodic table, there is a certain caveat about the periodic table I should have mentioned. It's called diatomic elements, and there are 7 elements on the periodic table that do not exist as just individual atoms. So when these elements are alone and they're not bonded into compounds with other elements, they exist as pairs, and we call those pairs diatomic elements. There are 7 of them. A helpful way to remember that is they kind of make a 7 on the periodic table, and then hydrogen. So it's hydrogen, nitrogen, oxygen, and then the halogens, fluorine, chlorine, bromine, and iodine. So those, if you're ever to just write them by themselves, not in a compound, you would write them as H2, N2, O2, F2, Cl2, Br2, or, oops, that's a typo. That's supposed to say I2. My bad. I2. Like I said, if you see a diatomic element in a chemical equation, know that the ion charge of the element is still what the periodic table says it's going to be. Don't get confused by that subscript 2. So like in this particular reaction, when I go to predict the products, beryllium is right here in the second column. That's why I know it's going to have a +2 charge. Nitrogen, even though it's diatomic and it comes as N2, the charge of a nitrogen ion when it ionizes will be -3 because it's here in the 5th column. And so from those charges, Be +2 and N -3, when I crisscross them, the 3 from nitrogen comes down and is beryllium subscript. The 2 from the beryllium comes down and is nitrogen subscript. I would predict product Be3N2. And again, it's ionic, so I'm going to say it's solid. That was a lot I just threw at you. I expect you to have questions on this. Please send them my way. Text me, shoot me an email, ask them in our Google Meets, and do your best with this. You're definitely well on your way to being a literate chemist, and keep up the hard work. Thanks, guys. See you when I see ya.